Chapter 9. I've done some editing of the PowerPoints, so your PowerPoints are not going to have everything that's in here. There may be one extra slide in my set, and there'll be added text and highlighting in this. That's just so that I stay on track. Okay, so this is our first introduction to we've learned what nucleophilic substitutions, bimolecular and unimolecular, and elimination bimolecular and unimolecular are. But now the problem is that reaction conditions, while they can favor any one of those, sometimes they are in competition. And we've got to decide which one is favored under certain conditions, and even select the conditions so that we can determine the outcome. And the next probably, let's see, I know 9 and 10 are going to be on this topic. 21, well, 13, okay. 1, 2, 3, 4. The first five chapters we're going to get into are chemical reactions. So this is where synthetic organic chemists would really just eat it up. But after we get through that, then we're going to shift over to analytical techniques. And I'm more familiar and happy with that one than I am with synthetics. But it's a necessary series of topics. Okay. So, see, I've already said that. We do consider that if one of the reactions is feasible, we have to consider all four of them, simply because they involve nucleophiles or bases. And the nucleophiles and bases, some kind can be the same, depending on the reaction conditions, can be the same species. It can be a base in one situation and a nucleophile in another. So we have to consider all four. If one of them is feasible, then we have to go to the mats with all four of them. Okay. I put this list up here. There are 6 factors that to be considered when we're looking at competition among the substitution and elimination reactions. And we're going to take those one at a time. After we consider this topic, one is, why do they compete? These reactions generally compete because they all involve a substrate containing a leaving group. That's one thing they all have in common. And I said this before, any species can act as a nucleophile or as a base, depending on the environment. Remember what we mean by a nucleophile. It's simply some species that has a lone pair available. It can be charged or not charged. And it's attacking an electrophile. So something wants electrons and the nucleophile's got them. And the electrophile is always a non-hydrogen. Okay. Whereas acting as a base, this same atom or molecule can act as a base, and it can be charged or not charged, and it attacks hydrogens. Okay. So we're looking at bases in terms of Bronsted-Lowry, where it accepts a hydrogen. So the two things they have in common is they all have leaving groups on the substrate, and they have an attacking species. So we generalize the attacking species so that we can discuss all four of them before we have to decide which one is which one is dominant. Then once we decide which one is dominant, we can call it a nucleophile or a base. Right, I think I already said that. Yeah. And just our terminology, just a reminder, unfeasible means it's not likely to occur. Doesn't mean it won't occur. It's just not likely to. And then feasible, it may occur, but it doesn't say anything about the relative rates. In fact, the discussion of reaction rates is where we break the ties among the different mechanisms. So here the attacking species is this acetate ion. And we know it's a nucleophile because it's attacking carbon, and the leaving group is bromine. Okay, so that particular reaction as described is an SN2 reaction. But it's possible that this reaction could undergo an SN1 type reaction if the bromine leaves first. And if the bromine leaves first, then the acetate ion can attack that carbocation. And in that case, since it can attack from the front or the back, you get a mixture of isomers. This one in particular, I think, because there's a methyl, ethyl. Okay, this is going to produce two diastereomers because you've got another stereo center there with that methyl group on the bottom poking out. Okay. So there are the two possibilities. Right, this is just an introduction to the possible competition between SN2 and SN1. Now remember, SN2s they're bimolecular. So the concentrations of both species have a bearing on the reaction rate. Whereas in SN1, the slow rate is the first step, which is unimolecular, and it depends on the leaving group. So that rate only depends upon the concentration of the substrate. Okay. I already said that. The principal factor that determines which is favorable over any other is reaction rate. Okay, there are a variety of factors that are that determine or control reaction rates. The identity of the attacking species and the substrate, right? And that is for E2s and SN2s, the bimoleculars, where you have to know the identities of both species. You can also have an influence from the choice of solvent. And we're going to look at these individually, one at a time, and they're going to be in our list here, 1 through 6. And by the way, so that you don't panic, I think I'm going to leave exams open book again. So we need to know the solvent, and we can favor one reaction over another by choosing the right solvent. That's going to come toward the end of the slide set. The concentration of the attacking species, and that depends on whether it's unimolecular or bimolecular as to which is important. And the temperature has a bearing also. There we go. So if we're trying to predict the outcome of this competition, we have to understand each one of the factors individually. First, we're going to just take a short detour and remind ourselves what determines the rate. Remember, the slowest step in any mechanism is the rate determining step. And for an SN2 reaction, it only has one step, right? Because it has a nucleophile attacking a substrate, or a nucleophile attacking a substrate. For the substitution reactions, that's true. So the rate is dependent upon both the concentration of the nucleophile and the substrate, whereas the SN1 reaction is unimolecular, and the slow rate is the leaving group, leaving. Okay, get that up out of the way. Wish I could do something about this. For E2 and E1, you have a similar situation. When we're discussing elimination reactions, now, if we have the same species, it may be a nucleophile for the substitution reaction, but now it's called a base because it attacks the hydrogen. And the bimolecular, since it's a single step, its reaction rate depends on both the base and the substrate, whereas the E1 depends on only the substrate leaving group concentration of the substrate, which has the leaving group. All right. Factor number one, the strength of the attacking species. The stronger the nucleophile, as you get stronger in the nucleophile, they call that nucleophilicity. The stronger the nucleophile promotes faster in SN2 reactions. So if there's a competition between SN1 and SN2, the strength of the nucleophile, as it gets stronger, you favor more and more the SN2 reaction. That rate increases. And these, I was unsure about the names of some of these, so I looked them up. That one's pyridine. Remember DNA and RNA, pyrimidines and pyridines, right? The next one, I looked, N3 is azide. Right, that's sodium azide. I don't know if they use it now, but they used to use it in airbags. And all you needed was a little shock, and it would decompose explosively into nitrogen gas. This one is thiocyanate, right? In NCS minus. We don't need to name the bromide and the chloride. This one's benzene thiolate. Benzene thiol. It's also called thiobenzene when it has the hydrogen. But I think the proper name is benzene thiolate. And that's increasing strength of the nucleophile. And of course, that's acetate. And then we have cyanide. Cyanide is the strongest out of this list. Now, this is an abbreviated list. It's not every one. It's just to illustrate the rate of the SN2 reaction and the favorability of the SN2 over the SN1 as the nucleophilicity increases. I got another slide on the other side. So you see there are other types of nucleophiles, and we have to consider them in relationship to their strength versus any others. And it's usually because a lot of the reactions occur in aqueous solution, we usually compare the strength of the nucleophiles with hydroxide ion as the central, like the anchor point. And anything stronger than hydroxide is considered a strong nucleophile. Anything weaker is a weak nucleophile. Now here's something called the Hammond postulate. And I'm not sure why they gave it a name unless they just wanted to honor some guy named Hammond or some girl. I don't know. It just says that for two elementary steps that are the same type, that is, uh, both are SN2 or both are E2, for instance, the one with the more negative value of delta G for the reaction tends to have the smaller energy barrier and tends to be faster. And that's really nothing new. I mean, we picked that up in general chemistry. We just didn't call it the Hammond postulate. In this case, we're comparing two possible reactions that are both SN2 or both E2. Or they could be both SN1 or both E1. As long as they're both the same mechanism that we're considering, then we look at the delta G for the reaction. Remember, if delta G is negative, it's considered spontaneous. But the more negative it is, or when you're comparing two delta G's for these reactions, the one that is more negative is the one that's faster. And this all has to do with the position of the reactants and products relative to one another. So here's an example. Say we have this SN2 reaction where we're going to substitute chloride for iodine or bromine for iodine. And we compare their energy diagrams. We notice that the activation energy for the chlorine substitution is much smaller than it is for the bromine substitution. And I think the reason for that is that the bromine is a more stable ion than chlorine is. Bromide is more stable than chloride because of its size. When you can spread the charge over a larger volume, that stabilizes the charge. So bromine starts at a lower energy. Right? The methyl iodide is going to be at the same energy. So in combination, both of them are at a lower energy. So it takes less energy to get over the hump. And they're both going to end up at roughly the same place. Since iodine is more stable than either bromide or chloride, because it's a larger atom, then you generally get the overall energy after the reaction at roughly the same position. So the difference between the two favors the delta G favors the chloride. The energy barrier is smaller. That's what I'm saying. And that's because chloride is a stronger nucleophile than bromide. Okay. If we compare this SN1 reaction, and we're looking at the leaving group, remember SN1 means that chloride has to leave first. And then we consider, what about the nucleophile, right? The thiocyanate versus the azide, right? We know that the azide is, I think it's stronger than the thiocyanate. Yeah, azide is stronger than thiocyanate. But remember, the slow step, the rate determining step, is the leaving, right? So the strength of the nucleophile has little or no effect on the outcome. The rates of both reactions are nearly the same. All right, so if we're looking at a comparison of SN2 versus SN1, strong nucleophiles tend to favor SN2 because they go in, and we've got both of the substrate and the nucleophile together, and the nucleophile has to go in and attack the non-hydrogen. that's favored by a stronger nucleophile, because the stronger nucleophile means you're going to get over that hump quicker. And it's a smaller hump, actually. It's a smaller activation energy. Whereas weak nucleophiles tend to favor SN1 reactions because they're totally dependent upon the leaving group leaving. Now, I'll be willing to bet that the SN1 reaction mechanism is slower than the SN2 reaction for any given set of conditions. So how do we determine the strength of the nucleophile? Well, there's some rules of thumb. Strong nucleophiles tend to have a total negative charge, which guarantees that they have, not only do they have the pairs of electrons, but they're unbalanced with the rest of the molecule. Whereas weak nucleophiles tend to be uncharged. And we've got them set up there in reds and blues. And the nucleophile strength increases to the right in this list because of the stability of the negative charge decreasing. That negative charge, when it's on something like a methyl group way out there to the right, that is very unstable because that's a primary carbon trying to hang on to that negative charge, similar to carbocations. It's trying to stabilize that charge and you just can't do it. So it's a very strong nucleophile. All right, so let's move on. So notice that carbanion out to the far right. If we substitute that for that strong nucleophile on our slide, if we substitute instead something on the ends of those bonds, put hydrogens up there, then you get that methyl anion. And the carbon atom is extremely nucleophilic when it bears a form of negative charge. It's called a carbanion. It possesses this lone pair of electrons that it can use to form a bond. Now, I think on the next slide, we're going to talk about it's extremely difficult to form that methyl carbanion because of the fact that you would have to remove a hydrogen. So when you remove a hydrogen, what are we talking about? We're talking about the pKa. Right? When a hydrogen leaves, that's a measure of its acidity. And for methyl groups and most alkanes, the pKa is huge. In other words, it does not want that hydrogen to leave. But it will accept the hydrogen, or if it's there, it'll accept any other atom to bond to. A deprotonation, therefore, for alkanes is unfeasible. It's very difficult to achieve, if at all. However, the pKa values for alkynes are much, much lower, approximately 25, which is still kind of high for normal acids that we consider. I think acetic acid is pKa of about 4.3 or 4, something like that. So it's much more acidic. It wants to get rid of that hydrogen. But with the pKa of around 25, it's much easier to remove a hydrogen from an alkyne. And that's what we're showing there. With that sodium hydride, the sodium is a spectator, and the hydride anion has that pair of electrons that it's taken one of them from sodium. So it can strip off a hydrogen from that alkyne. And remember, the effective electronegativity increases as you add pi bonds. Right? So the alkyne has a much higher electronegativity, and it's going to make that hydrogen on the alkyne carbon more available. So that hydrogen can come in there from sodium hydride and strip off a hydrogen and make an alkanide anion pretty easily. That makes it a strong nucleophile, and now it can attack the substrate, and the leaving group then is easily removed. And we're still talking about SN2 versus SN1. Strong nucleophiles tend to favor the SN2. So there we have an SN2 reaction at the bottom of the page. But we had to create that nucleophile. And my guess is you're not going to find that nucleophile sitting on your chemical bench, on your shelf. Right? You have to make it in situ. So you would add the sodium hydride to the alkyne and immediately add your substrate. Okay, let's talk about comparing E2s and E1s. The E2, since it requires, the rate is dependent upon the substrate and the base concentrations, then the E2 rate should increase with the strength of the base. As the base strength increases, the rate should increase. And we're talking about anything that will accept a proton. So there you have the acetate ion on the left. It's given a relative reaction rate of 1. The pyridine is a little faster. The phenolate ion, right? Phenol, remove the hydrogen. The phenolate ion is much, much faster, over 10 times as fast as the pyridine. And then the tertiary amine has a very, it's very strong. It's high basicity. And then the hydroxyl is stronger than any of them. Now, how do we know that hydroxyl is a strong base? Because the conjugate acid of hydroxyl is water. And water has a pKa 14. Okay, so remember, the conjugate base of a weak acid is a strong base. So it's no surprise that hydroxyl would be, we'd consider it a strong base. And in fact, for organic chemistry, there are stronger bases than hydroxyl. Okay, so the E2 reaction rate increases as the base strength increases. And the stronger the base, let's see, is that coming up? I guess it'll come up in a minute. I was going to say, the stronger the base, strong bases favor E2 over E1. So here we have acetate attacking this dichloroethane, and it's going to go in, pluck off a hydrogen, and form a bond with that hydrogen, and the electron pair from that hydrogen-carbon bond is going to go make a double bond. So here we've got a comparison of two bases, the acetate versus the hydroxyl. And they're both going to produce the same product. But which one's faster? The second one should be faster. 9-14 should be faster because the base is stronger. And this is Hammond postulate strikes again. The instability of the hydroxyl, in other words, its strength as a base, sets it at a higher energy level than the acetate. So they're going to end up in the same place. We're going to have, we're going to have the same product, the effect on the substrate. We're going to have protonated bases, of course, at the end, but they're going to be at the same, relative same energy position. The difference is the the energy of the reactants. We start off with a stronger base, which puts it at it's more unstable. It's at a higher energy level. So the reaction is faster because the energy barrier is smaller. And the free energy would be more negative. So the rate of an E1 reaction we know is independent of the strength of the base because like the SN1, the leaving group has to leave. In other words, the hydrogen has to leave first. No, excuse me, the leaving. Well, let's see. Yeah, the hydrogen would be the leaving. Strong bases tend to favor the E2 reaction. In other words, they go in and pluck off that hydrogen readily. And here's where we draw the distinction. You know, what do we mean by a strong base? Well, if it's stronger than hydroxyl, then we're going to favor E2. If it's weaker than hydroxyl, we're going to favor E1s. So let's see. We've only looked at E2, right? Yeah, E2. We should have a slide on E1 coming up. Well, okay, E1, the hydrogen would leave first, wouldn't it? Where would it go? Right? Hydrogens don't exist independent. Right? They have to go somewhere. Okay, so let's see if we learn anything from this. Is phenoxide ion a strong base or a weak base? Will it tend to favor E1 or E2 mechanism? So the questions we have to ask is, what's the pKa of phenol? Because the conjugate base of the phenol will be relative to the pKa of phenol, the phenolate ion, or the phenoxide anion, excuse me, phenoxide. How does this compare to that from the conjugate base of water? Well, the pKa value for phenol is 10, and that for water. So the phenoxide ion would be just the opposite. Since it's a stronger acid, it'll be a weaker base. So the phenoxide ion is a weaker base than hydroxyl. So the E1 reactions are favored by weak bases, whereas the E2 reaction is favored by strong bases. So in this case, the phenoxide ion, we would favor the E1 reaction over the E2 reaction. The other deciding, now we've looked at SN1 versus SN2 and E2 versus E1. Now we're going to look at E2 versus SN2. So the bimolecular comparisons here. What type of reaction are you going to have? Well, if you have a strong nucleophile, that can also serve as a base. And in this case, we have the butoxide ion. All right, 4 carbons, tertiary butoxide. You've got those methyl groups sticking out there. They're bulky. They're in the way. And steric hindrance now plays a role. And we're still talking about the strength of the attacking species, but we're introducing this steric hindrance as a subtitle. Let me put that up there. Steric hindrance. What influence does that have on the effect of the strength of your nucleophile or base? Well, remember, a nucleophile has to attack a non-hydrogen. So if it's attacking this carbon with its leaving group, the reaction is going to be very slow. Why? Because those bulky methyl groups are in the way. It can't get at the carbon easily. So in this case, the E2 reaction is going to be favored. Instead of attacking the carbon, that tertiary butoxide ion is going to attack the hydrogen, which is sticking out there just waving. So if there's steric hindrance involved, the E2 is going to be favored over the SN2. There's the tertiary butoxide ion. There are other possibilities, and we can use this effect to favor one reaction over the other. These strong, bulky bases, neopentoxide anion, lithium diisopropylamide, LDA for short, has lots of bulk around that nitrogen. And the lithium, in this case, is a spectator. Actually, the butoxide and the neopentoxide anions, they have to have spectators too, because our reaction solutions can't be charged, right? In chemistry, we don't deal well with static charges. That's physics. So the charges have to balance somehow. So we need a counter cation for those other, the tertiary butoxide and the neopentoxide anions. Okay, next factor, concentration of the attacking species. Okay, that has a bearing on which one of these mechanisms is favored. Well, since SN2 and E2 reaction rates are dependent, their reaction rate is dependent upon the concentration of the attacking species, it's only logical that that concentration will have an effect. Whereas the SN1 and the E1 are not dependent on that rate, on the concentration of the attacking species. That was fairly simple, actually. So if we have a high concentration of a strong nucleophile or a base, that will promote the faster SN2 or E2 reaction, favoring them over the SN1 to E1s. Low concentrations of a strong nucleophile or base will promote slow SN2 or E2 reaction, leaving the SN1, E2 reactions favored. That doesn't mean it's going to happen any faster, right? Because everything's dependent upon the leaving group leaving. So it's all substrate concentration. So the weak nucleophile or base tends to favor the SN1, E1 reaction, regardless of the concentration of the attacking species. Now here's a interesting point to remember when we're writing out the sequence of reactions toward a product. You may assume that a high concentration of an attacking species is present unless it's deliberately made dilute. And those conditions are usually placed above and below the arrow in a reaction equation. All right. So which of these reactions, SN2, 1, E2, or E1, are favored first by a high concentration of sulfhydryl ion, and B, a low concentration of that ion? Right? So first of all, is that attacking species a strong nucleophile or a weak nucleophile? Is it a strong base or a weak base? Then we have to decide which reactions are favored by high concentrations of attacking species and which are favored by low. We just covered that on the previous slide. So we really need to know, is this a strong nucleophile or a strong base? So the way to find that out is to look at the conjugate acid for the HS minus ion, which would be H2S. The pKa for H2S is 7.2, which is significantly lower than 14 for water. Remember, we're comparing this with hydroxyl ions. So that means if 7.2 is smaller than 14, so the HS minus, there's Galen, the HS minus should be a weaker base than OH, or weaker nucleophile. A high concentration then of this, well, wait a minute, it's calling it a strong nucleophile. Okay. Did I mess up? Let's see. HS minus is a weak base, yes, because it's significantly weaker than OH. Okay, so we determined that HS minus is a weak base. It's a weak base. Oh, we're looking at substitutions also. So we have to say, what kind of nucleophile is it? Is it a strong or a weak nucleophile? In this case, it's charged, and it has, in fact, I think it has six electrons, 6 available electrons. So this should be a strong nucleophile. It's charged. That's the first thing. A negative charge is likely to make it a strong nucleophile. So because it's a strong nucleophile, high concentration favors SN2 over SN1. So it's going to attack the non-hydrogen, while low concentration favors the SN1. And because the HS minus is a weak base, it will favor the E1 over the E2, regardless of the concentration. All right. Fact number 3. Is leaving group ability. You know what? I'm going to modify that a little bit. Leaving group stability. The more stable the leaving group is upon its departure, the better it is as a leaving group. Here's one good example. This, any alkyl tosylate, it will have that red part on it, and the R group is carbon and whatever else. So the leaving group is this OTS, we abbreviated. And its ability to leave is much faster than a simple alkyl chloride. It leaves more easily than the chloride ion does, 300 times faster for an SN2 reaction. But its ability to leave for an SN1 reaction is 33 times greater than it is for an SN2. So as compared to chloride. So that tells me that it's an extremely good leaving group, would favor the SN1 over the SN2 if it's present on your substrate. And here we have a comparison of SN2 reaction rates for hydroxyl as the attacking species, and then the different leaving groups. So as far as the SN2 reaction goes, hydroxyl would not be a good leaving group, especially if you're attacking with hydroxyl. That doesn't make any sense. The amine leaving or the alkyl oxide ion leaving, they're pretty poor. Fluoride is a little better, not much. Chloride's a lot better. Bromine's hugely better, and iodine's even better than that. And that's because of the stability of a leaving group. Remember, we're spreading for the single ions, you're spreading the charge as you go down in that halogen group. The ions are getting bigger. So we stabilize that single negative charge over a larger volume. And then we can do the same thing, only now the tosylate, we're stabilizing that charge. Let's see. Yeah, it's charged. We're stabilizing that charge not only with the size of the molecule or the ion, but it also resonates. We can resonate that negative charge over those double bonds in that phenyl group. So the tosylate ion is a very extremely good leaving group. And then if we compare the pKa of the conjugate acid, in other words, just add a hydrogen to each one of those, the SN2 reaction rate increases as the pKa of the conjugate acid decreases. It makes a more stable, a weaker base. Remember, a strong acid produces a weak conjugate base. A weak conjugate base means that it doesn't want hydrogens. So if there are any hydrogens around, it's not going to take them. So how about an SN1 reaction? The effect is even more pronounced for SN1 reactions because the rate is dependent upon the the ability of the leaving group to leave. And SN1, if the leaving group is more stable after it leaves, then the SN1 is going to be more favored. And this says nothing about the attacking group. This is only about the leaving group. And so if we have the same attacking group, then the ability of the leaving group, the stability of the leaving group will favor, I think, SN1 over SN2. Okay, so now we are going to compare the two. So relative leaving group abilities are governed largely by the stabilities of the leaving groups and form in which they come off the substrate. And that's another way of saying that how stable is the leaving group after it leaves? That means that it's a good leaving group. For SN1s and E1s, the leaving group has to leave first. And the SN1 and E1 are very sensitive to the leaving group ability because that's the rate determining step. The better the leaving group, the faster the SN1 or the E1 reaction. The leaving group in SN2 and E2 is assisted by the attacking species. So the stronger the nucleophile or the stronger the base, the better the leaving group can leave. Okay. So if we can stabilize the charge of the leaving group after it leaves, then we make a better and better leaving group. If we have a good leaving group, then that's our first condition. We look at the leaving group. If the leaving group, actually, we're going to look at different steps for, it's like a decision tree. What do we consider first? I know we've talked about them in this order: strength of attacking species, concentration of attacking species, and leaving group stability. But when you go to make a decision, your focus is first on the leaving group. Do you have a good leaving group? If you've got a good leaving group, then all four of these possibilities are feasible. Whereas with poor leaving groups, only the SN2 and the E2 reactions tend to be feasible. All right. With an unstable leaving group, all tend to be unfeasible. So there you have sort of a wordy decision tree. Good leaving groups favor all four. Poor leaving groups favor only the bimoleculars, and unsuitable leaving groups favor none of them. Then none of them will be feasible. Now, better leaving groups tend to be weaker bases based upon the strong conjugate acid. So if the conjugate acid has a very low pKa, you're looking at the conjugate base as a very good leaving group. How about sulfonate anions? What's a sulfonate? Well, there are examples there. Sulfuric acid. The first proton leaving sulfuric acid produces a bisulfate anion. We would call that a hydrogen sulfate properly. But bisulfate is still part of the vernacular, so we have to use it sometimes. Methyl sulfonate or mesylate is a better, is a weaker base. The tosylate is a weaker base than that, and the triflate, which has a carbon. It's like the methylate, only the carbon instead of hydrogens has fluorines on it. All right. So how would you convert a poor leaving group into a good leaving group? Well, here's an example. 1, 2, 3, 4. So that's butanol, butane 1-ol, and sodium bromide. So sodium is the spectator, bromide is the attacking species. In water, you get no reaction. However, under acidic conditions, the reaction does take place. Now, why is that? Well, if we look at hydroxide is not a good leaving group. Right? Hydroxide ion is not a good leaving. Why? Because it's a very strong base. And it's going to, it's good attacking group, but it's not a good leaving group. It's not stable in and on its own. So if we acidify the environment, and instead of using sodium bromide, we use, in an aqueous solution, we use sulfuric acid and hydrobromic acid, then we get the ability now of the bromine to replace the hydroxyl. In the next page, we're going to show you the mechanism that explains that. In an acidic environment, we transfer a proton. The butane 1-ol becomes the attacking group, and we get a proton transfer. Now that we've got that potential for water as a leaving group, water would be an excellent leaving group because H2O is infinitely stable in aqueous solution. Now in that acidic environment, we have a good leaving group, and the bromine can attack the neighboring carbon and the water can leave. So that SN2 reaction now is feasible under acidic conditions. But notice, let me go back. Notice you have to reflux it for 90 minutes, right? So it's not that it's an instant reaction, but it's feasible now rather than non-feasible. So How about alcohols as leaving groups? So what would the leaving group be for that substrate? Well, we know that the OH is not going to leave, but maybe methanol might be a good leaving group. Could it possibly be a leaving group? Well, in neutral environment where you have sodium and bromide, remember the pH of this solution, if we only have aqueous solution and sodium bromide is the product of a strong base and a strong acid reaction, right? So that means the solution is going to be neutral. Remember that from general chemistry. But if we make it acidic, we do get the reaction, and we can cause the methane to leave. It can be attacked by the bromine. So the mechanism for that one, and this is again under acidic conditions, the mechanism for that one is a proton transfer. If you transfer a proton to that oxygen, that ether, the ether oxygen, now what's the leaving group? Now the leaving group is that phenol-bound molecule. I'm going to try to name it right now. And the bromine can attack the methyl carbon. And so now what do you have left? Well, the proton was transferred to the oxygen, and the methane group is leaving. So now you have a, let's see. There's a common name for that. I just can't remember it right now. Well, it's a Benz 1,2-diol. How about that? But we've created a leaving group in the reaction environment simply by acidifying the solution. So there we were introduced to proton transfers. Proton transfer can facilitate elimination reactions also. We were looking at SN2 reactions, but E2 reactions can also benefit from proton transfer by generating a good leaving group. And that will produce what's called a dehydration. In other words, dehydro means remove water. So by proton transfer to that hydroxyl, now we have a good leaving group, and we're going to leave behind an electron pair that can form a pi bond within that cyclohexane. It has to be an acidic environment, though. So the first proton transfer, the oxygen attacks the hydrogen on the weak acid. Remember, phosphoric acid is weak. It's a weak acid. Now, that's not to say that in chemical terms, if you stick your hand into a beaker full of concentrated phosphoric acid, it's going to do some damage, right? In fact, what are some of the ingredients of Coca-Cola? Phosphoric acid is one of them, right? It's not just carbonation that makes carbonic acid. Phosphoric acid is in there, and if you take a bottle of Coke and drop a nail in it, come back a week later, the nail's gone. So it may be a weak acid, but it's still corrosive. In this case, though, we get a proton transfer, and now we've produced water as a leaving group on that cyclohexane. When that water leaves, right, heterolysis is the step that we're looking at. When that leaving group leaves, now we can transfer another proton to a water molecule and create the double bond. And since it's an acidic environment, remember we talked about incongruities of environment and reactions we expect, right? We can expect the formation of hydronium ions in this mechanism because we are in an acidic environment. So there's no dichotomy there. So this three-step mechanism, proton transfer, heterolysis, followed by electrophile elimination, produces the desired product. How about amines as leaving groups? Well, let's see. Again, we're a neutral environment with sodium bromide versus a hydrobromic acid, you know. And amines tend not to undergo nucleophilic substitution or elimination reactions under normal conditions. That's a fact. Protonation of the mildly basic nitrogen of the amino group, which can take place, would make the leaving group better, but even under acidic conditions, amines tend not to act as substrates in nucleophilic substitution or elimination reactions. So what we're saying is that nitrogen, even though it's positively charged, is going to stay put. It's not going to leave, because when it leaves, it's not stable. If it leaves, it's not stable. All right, so amines are not good leaving groups, even under acidic conditions. Okay, fourth factor. We're halfway there. Type of carbon bonded to the leaving group. Type of carbon, and here we're talking about sp3, sp2, sp1. Type of hybridization, type of carbon bonded to the leaving group. So everybody remembers what we mean by sp3, sp2, and sp1 hybridization. I shouldn't have to go back at that one. But the point that we're making here is that sp2s and sp hybridized carbons tend to form stronger sigma bonds than sp3 hybridized carbons. Okay, here's one way to look at it. When we're looking at the strength of sigma bonds, oops, from H and P backwards. The strength of sigma bonds versus, let's see, let's put sp on top, sp2 here, sp3 here. And the strength of the sigma bond that can form with a carbon, this is carbon, 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 increases this direction. The way I look at it is the S versus P character of the hybridized bond, right? This hybridized bond has 50% S character, whereas this one only has 33%, 33.33% S character. And this one only has 25% S character. When you're talking about overlap of orbitals to form the bonds, you get more overlap with this 50% S character than you do what's left over, right? 50% P character or 67% P character or 75% P character. Remember, the P character tends to elongate the orbital and you get less overlap. So I think that that is one explanation for the strength of the sigma bond with sp and sp2 hybridized versus sp3 hybridized carbon. So what does that mean? A stronger bond with the sp2s and sps make it more difficult for the leaving group to leave. If you can strengthen that sigma bond, then you make it more difficult for the leaving group to leave from a carbon that has a pi bond, 1 pi bond, or 2 pi bonds. That's what we're talking about here. So that's the type of carbon bond, type of carbon bonded to the leaving group. Type of carbon bonded to the leaving group. That's important. Bonded to the leaving group, not part of the leaving group, but bonded to the leaving group. Tends to strengthen that bond and make the leaving group less likely to leave. So here's another explanation. That was my thought only. That's not Carty's thoughts. But there's further hindrance for an SN2 reaction because you have to have a nucleophile attack that carbon. And when it's approaching that carbon, what is it going to see? It's going to see more electron density around that carbon because of the pi bond. Remember, the pi bonds are out here. Sigma bonds are in here, right between the carbons. And pi bonds are out here. So you have more electron density out there, hindering the approach of the nucleophile. So the nucleophile can't get at the carbon because of electrostatic repulsion. That's the whole point of that slide. Okay. So what effect do they alkyl groups on the rate of SN2 reaction? Well, if we look at the substrate, and now we've well, actually, this limits my discussion by the type of carbon. This is one type of carbon. There are other types of carbons, such as the primary, secondary, and tertiary carbons. And that has to do, let's see, primary, secondary, tertiary carbons. Add that to my list. So the type of carbon bonded to the leaving group, if it's an SN2 reaction, then we have the attacking group going after that carbon. And the substrate, the reaction rate tends to increase for less substituted carbons. The number of alkyl groups on the carbon atom to which the leaving group is bonded decreases rates as you increase the number of bonded groups to the carbon. Right, so that's why we see that from left to right, the SN2 reaction decreases with the more methyl groups that are on that carbon. And we've got the same leaving group, we just have more methyls there instead of hydrogens. Now here's the explanation. Steric hindrance. Right, that nucleophile has to, in order to have an SN2 reaction, the nucleophile has to attack the carbon before the leaving group leaves. If we have no methyl groups, just hydrogens, that carbon is wide open. And as we add methyl groups, we hinder further and further the approach of that nucleophile. So that decreases the reaction rate for the SN2 reaction. Steric hindrance, pure and simple. Oh, let me mark Galen zoomed in. Where did you go? She may drop it. I don't know in the summer how long you have to make a deposit on your bill. Right. They administrate, yeah, in the summer. they could administratively drop. And I don't know if he's out of pocket or student assistance. Okay. The reaction rates are so slow for tertiary carbons that you effectively say that that reaction doesn't happen. Tertiary substrates do not have SN2 reaction products. Now, for an SN1 reaction, the SN1 reaction rate increases with the number of carbon substitutes. Substituents attached to the carbon. Now, why is that? Well, think about it. The first thing that has to happen in an SN1 reaction is the leaving group has to leave. And what does it leave behind? It leaves a carbocation behind. So what you need is a stable carbocation in order for that reaction, that rate determining step to be faster. You need a stable carbocation. The more stable the carbocation, the faster the rate determining step for an SN1 reaction. So the more substituted the carbon, the more stable the carbocation. So it's just the opposite of SN2. So we should see an increase in rate from methyl to primary to secondary to tertiary carbon substitution. And in fact, it's a very sharp increase. In fact, there's such a huge difference that methyl substrates and primary substrates don't produce reaction products. There's just not enough stabilization of the carbocation. So the SN1 reaction doesn't occur. We're going to get to E1s in just a second. Actually, you know what? We can talk about both of them. Since they're both dependent upon the stability of the carbocation afterwards, then either SN1 or E1 reactions don't occur for methyl and primary substituted carbons. And they increase dramatically for secondary and tertiary substituted carbons. So what we're doing is we're gathering reaction conditions and decision conditions that we can put in our quiver and pull out and decide which reaction is favorable. We just need a method for bringing all this information together. As soon as we get to number 6, we'll do that. Okay, so here we have A and B molecules, and we have the tosylate is our leaving group. Right, so we know that's the one that's going to leave, and it's going to leave from that benzyl carbon. Okay. So which one will undergo an E1 reaction faster? Well, I think obviously E1 requires that the leaving group has to leave. And that we picked a very good leaving group, right? The tosylate anion is a very good leaving group. So it's going to leave behind a carbocation. On A, the carbocation is going to be on a secondary carbon. Whereas for B, the carbocation is going to be on a tertiary carbon. It should be more stable. So B should be favored for an E1 reaction. It should be faster, much faster. And there's the picture description. Stabilization. You probably get some stabilization from the phenyl ring, right? But still, the tertiary carbocation is going to be much more stable than the secondary. And that makes for a faster E1 mechanism. That was easy. How about E2 reactions? Well, since we're talking about a base attacking a hydrogen on the beta carbon, or should that be? The alpha carbon is next to the leaving group. The beta carbon is where the hydrogen is located. So the base attacks the hydrogen. And so what's going to hinder that base from attacking the hydrogen? If it's primary, secondary, or tertiary? Nothing. Nothing's going to stop it. Nothing's in the way. There's no steric hindrance. If it's the same base, it's attacking roughly the same type of hydrogen on a methyl group. So E2 reactions tend to be insensitive to the number of alkyl groups that are on the carbon bonded to the leaving group. Okay. This is a summary of the number of alkyl groups in the carbon. All right, so the number of alkyl groups bonded to the carbon for SN2 reaction so we'll get an SN2 reaction for either methyl, primary, secondary. Tertiary, there's too much steric hindrance, right? SN1 reaction, the methyl and the primary substituted carbons will not undergo an SN1 simply because the carbocation is not stabilized. And we can say the same thing for the elimination reaction. The SN1 versus the E1, they have well, okay, I just read my own point. E1 and E2 on methyls make no sense, right? Since there's no secondary carbon to form a pi bond with, right? So we probably should have put a big X in those. E1s and E2s, put a big X for the methyl. But the E2 is stabilized the same way as the SN2, aside from the fact that you can't form a double bond with a single carbon. And then the E1 and the SN1 are similar in their reaction rates for secondary and tertiary, because the carbocation has to stabilize, has to be more stable. So that's a summary of everything we've discussed so far. Okay, now we're going to look at types of carbons. We're still on types of carbons. Now we're talking about resonance stabilization. So let me tell you what, I'm going to move these down here so I can put another one in here. Resonance stabilization. We're still talking about the type of carbon bonded to the leaving. So, if the leaving group is bonded to a primary allyl or benzyl, when we say allyl, what does that mean? Allyl is a terminology for, this is an allyl carbon, right? It's next to, it's sigma bonded to the carbon that's in a sigma double. So this is the allyl carbon. And the leaving group is bonded to this allyl carbon. Or in the secondary case, the benzyl carbon, which is the first carbon off of the benzene ring. All right. So what can form if the leaving group leaves? Now we're talking about probably SN2 versus SN1. If the leaving group is bonded to a primary allyl or benzyl carbon, then both the SN2 and SN1 reactions are feasible. And the reason for that is, well, let's take the SN1. The leaving group. If the leaving group leaves, what's left behind? A carbocation. The carbocation can resonate with this double bond. Okay, and that stabilizes it. Similarly, if the leaving group leaves off of the primary benzyl carbon, then it's resonance stabilized with the benzene ring. We don't show all the possibilities there, but they exist. And that stabilization of the carbocation means that the SN1 is more stable. But also, what about SN2? Which carbon is going to be attacked? For an SN2, the allyl carbon is going to be attacked, or the benzyl carbon is going to be attacked. Let's see. Well, that didn't give me much explanation. I mean, that explains the SN1, but how about the SN2? I don't see an explanation for that one. Must be in the textbook. Which substrate, A or B, would undergo an SN1 reaction faster? Okay. What type of carbocation would substrate A produce in the rate determining step? If this is SN1, then chlorine has to leave first. That will produce a carbocation for both A and B. And is it stabilized, more stabilized for A than it is for B? And the difference between the two is obviously that oxygen. Right? Will that oxygen stabilize a carbocation? All right. So for A, for an SN1, we get a strong resonance stabilization because that oxygen has donatable electron pairs. And we can move the positive charge onto the oxygen. Right? Whereas with the B molecule, all you get is a secondary carbocation that is much less stable. So A would be favored in this case. A would produce the faster SN1 reaction. Okay, now 5 is solvent effects. Right. And I'm just going to go ahead and put 6 down here. Temperature is the last one. Okay. Okay. When we talk about solvent effects, we're drawing a distinction between protic solvents and aprotic solvents. And when we say that, what we mean is protic solvents have the capacity to form hydrogen bonding with the attacking group, whereas aprotic solvents do not. Okay. So what effect does that have on the choice of reactions? Well, aprotic solvents tend to favor SN2 and E2 reactions because they don't hinder the approach of the nucleophile or the base. Right? They don't form a hydrogen bond. They don't surround the nucleophile or the base with hydrogen bonded water molecules or any other type of protic solvent like alcohols, like methanol or ethanol, so forth. That would hinder the approach of the nucleophile or the base. And remember, for the SN2 and the E2s, their reaction rates are dependent upon the concentration of the nucleophile or the base. So if we hinder their approach, that effectively reduces their concentration for protics. But so for aprotics, we get the concentration that's actually the nominal concentration we established for the reaction for the nucleophile of the base is still there because the aprotic solvent does not interfere with the nucleophile of the base, whereas the protic solvent does interfere, and they tend to favor the SN1 and E1 reactions because they're not dependent upon the concentration of the nucleophile or the base. So this is what the protic solvent would do to your nucleophile. We call it hydration. It's hydrated, surrounded by water molecules. Whereas the aprotic solvent, in this case, acetone, right, does not solvate the nucleophile. Okay, let's see. I think I've explained it already. We're not going to beat that horse anymore. This just puts it in black and white. Okay. All right. So what do we consider protic solvents? Well, I mentioned water, obviously. Methanol is a good protic solvent, right? It has that the hydrogen bond donor. Excuse me. And there are others. Ethanol is a good one. Anything with alcohol groups on it would be a good protic solvent. As long as it's not sterically hindered, then it will work. Aprotic solvents like acetone, DMSO, dimethyl sulfoxide. That's an interesting compound. Dimethyl sulfoxide, if you just put a tiny drop and it drops on your finger, you can taste it instantly. It's that soluble in your system. It goes straight to your tongue. DMF, dimethylformamide, and well, one way to say it is methyl cyanide, but that pricks people's ears. So I think we call it there's another name. Why can't I remember it? Hopefully it'll come to me later. But the SN2 reaction rate as given, where we're reacting the azide ion with 1, 2, 3, 4 butane 1 bromobutane is the substrate, and the azide ion is the attacking group. The reaction is very slow in protic solvents and much, much faster in aprotics for the SN2 reaction. Substitute the azide group for the bromine. For the SN1 reaction, which doesn't depend upon the does not depend upon the concentration of the attacking group. It just depends on the ability of the leaving group to leave. Well, what stabilizes the leaving group? If you have iodide out there, that ion, and you have an aprotic solvent, there's nothing to keep it in solution effectively. But if you have a protic solvent, the solvation will keep that iodine more stable in solution. So it's just the opposite effect. For the SN1 reaction, protic solvents increase the rate of reaction dramatically because they stabilize the leaving group. And then they open up the carbocation for attack by the nucleophile. So it's just the opposite. If you want to favor one versus the other, just change the solvent. Okay. This is just a relative arrangement of nucleophiles and their relative rates of reaction depending on whether it's an well, actually, okay, I see it's a stacked table, right? If you could take the bottom two rows and pull them out to the side, then you'd have the complete table. So you follow the top one along for an SN2 reaction, and you keep going through the azide, and you go to the bromide, you go to the methoxide and cyanide, and just keep going. Then you find that for SN2 reactions, the strength of the nucleophile in a protic solvent, remember this is ethanol. This reaction is in ethanol, and it's an SN2 reaction that we're describing. As we increase the strength of the nucleophile, we still increase the rate of the reaction, even in a protic solvent. And that's based not upon the nucleophile, but upon the stability of the leaving group. So if the leaving group can be stabilized by, let's see, yeah, the bromine in ethanol is about 30 times greater, the rate of the reaction based upon the nucleophilicity of bromide in ethanol is about 30 times greater than chloride because of its stability after it leaves. In a protic solvent, it's more stable. Whereas in DMF, dimethylformamide, aprotic solvent, the chloride is stronger nucleophile than the bromide. So this reversal occurs simply because of the stabilizing effect of the protic solvents. Since chloride is a lot smaller than bromide, it means that the negative charge is more concentrated when it's on chloride than it is on bromide. Okay, and here we're looking at the top in black and the bottom in blue. So we're looking at the free energy diagram. So we're looking at the difference. The chloride in aprotic solvents is a stronger nucleophile than bromide. But in protic solvents, the bromide is a stronger nucleophile because the chloride has a more concentrated negative charge. It's more readily protonated, not protonated, hydrogen bonded than the bromide. So you get a switch in the strength of the nucleophiles. And that's what I'm trying to say here with these addeds. And this occurs for single atoms. It can't, in other words, we cannot resonance delocalize. When you have the ability on larger molecules to delocalize, then that's another animal. Now, if we have single atoms that are ions in the same period, in that same row, then they don't switch. They retain their nucleophilicities in either protic or aprotic solvents. Okay, the last one is temperature or heat. That seems redundant. Okay, the conditions that favor an SN2 reaction are similar to the conditions that favor an E2 reaction. So SN2 and E2 products are often formed together. Right? That can be a problem. Right? If you're expecting one reaction type over the other and you get an equal amount of both, then that requires that you've got to go through separation procedures. So is there any way that we can favor one over the other in SN2 or E2? Similarly for SN1s and E1s, but we're going to talk about SN2s and E2s for this slide. Okay, what we find is that when you increase the temperature of the reaction, you tend to promote the elimination more than the substitution. So if we have this situation where we're going to substitute hydroxyl for a bromine, and but we'd rather have the elimination product, right? Where we where we attack a hydrogen, and then the bromine leaves, and its electron pair leaves behind and forms the pi bond. Then we want to favor that one over the SN2. Then if we find that if we increase the temperature, we do favor the E2 reaction, the products. Okay, so why is that? Well, the best way to look at it is in terms of Gibbs equation. Right, delta G equals delta H minus T delta S. When we talk about entropy in these terms, for the substitution reaction, you get only two products as a consequence. So we really haven't changed the entropy much because we've got an OH attacking and we've got the 2-bromopropane, right? We have two there, and we've got two products in the two products as outcome. We haven't changed this value much, the entropy. But if we do a substitute, we do an elimination reaction, we're increasing from 2 to 3. We're producing greater entropy. So if this term increases, what would favor that term? What would give us a negative here? Almost guaranteed. Higher temperature. You increase the temperature and you favor, you make the delta G negative by increasing the temperature, and whatever delta H is involved is very slight difference. So by under conditions of high temperature, delta G tends to be negative, and that favors the reaction rate for the elimination rather than the substitution. Okay, now that we've got all those terms, factors identified, what do we do with them? In fact, I think I don't have the video embedded in my slide set, but there's a video in Brightspace by Professor Dave. You ever seen Professor Dave's? Yeah. His earlier versions where he's got long hair and tattoos and stuff, those are the better ones. The ones he's making these days, he's cleaned up and he's slid off the deep end. He's in the far left aisle. So he's one of those with TDS. So what's our first step? Determine whether these reaction types are even feasible. So that's step one. feasibility. Feasibility of the reactions, right? You need a good leaving group. Should be at least as stable as fluoride ion. Unsuitable leaving groups would be hydroxides, would be alkyl oxides, amines, hydrides, or any alkyl anions. Those are not suitable. If those are the leaving groups, then you can pretty much eliminate that reaction. The decision doesn't need to be made. In other words, you can stop here. Also, the leaving group should be bonded to an sp3 hybridized carbon because you don't want that sigma bond to be too strong. Okay. And you need an attacking species that is either a nucleophile or a base. Right? If it's one or the other, then we're going to make a decision. We're going to say, remember the first condition, earlier slides. If one is feasible, then we have to consider all of them. So if we have a good nucleophile or a good base, then we have to consider both all the S's and all the E's. Okay, so with our example up here in the top, and we're in a non-protic solution, we've got sodium bromide. So that's a neutral non-protic solution. Leaving group is chloride. That's suitable, right? Chloride's good. It's a better leaving group than fluoride. Chloride is attached to an sp3 hybridized carbon. Yes, it is. Okay. Bromine is an attacking species. Right? It's a good attacking species. It's a good, let's see, a good nucleophile. Right? It's not necessarily a good base, but it's a good nucleophile. Okay. So after we've decided that in this reaction, we have to consider all four possibilities, rule out the unfeasibles. Step 2. Rule out the unfeasible. Spell that right? No, it's IBL. Never have got that one right. Able versus Ibble. If it's a tertiary carbon, you can't consider an SN2 reaction because of steric hindrance. Right? So we can rule out SN2s for tertiary carbons. If it's a primary or methyl carbon, we can't consider SN1 or E1 unless there's resonance stabilization. Okay. And then E2 and E1, if there are no beta hydrogens. If there are no beta hydrogens, you can't form a double bond. Well, actually, there's no hydrogen to attack. If there are no beta hydrogens, that's the whole purpose of the base. It's got to attack a hydrogen on the beta carbon. So if there's none there, then you can throw E1 and E2 out. So it's important relative to our sample equation there. We can't rule out any of the reactions from the types of substrate, from the leaving group ability, or the absence of beta hydrogens. The solvent is aprotic. That means we can rule out SN1 and E1. Because only the protic solvents stabilize the leaving group. That's why SN1 and E1 are not good candidates for this reaction. So we're looking at SN2 or E2 for this particular reaction. Okay. Then you say favored by, what's that term? Favored by attacking species. Which are favored by attacking species. SN2 is favored by a strong nucleophile. SN1 is favored by a weak nucleophile or by low concentrations of the strong nucleophile. So remember, we have to assume that this bromide is high concentration because we did not say dilute. E2 is favored by a strong base. E1 is favored by a weak base or by a low concentration of a strong base. So the attacking species is bromide. It's a strong nucleophile, which favors SN2 over SN1. All right, so strong nucleophile is favored by the bromide ion. Bromide is a weak base, which favors E1 over E2. So we've got a decision between SN2 versus E1. So which one is favored? Since E1 is unfeasible, why is E1 unfeasible? We just said on the previous one, didn't we? E1 is favored by a weak base. This is a strong base. Oh, excuse me. No, this is a weak base. So we got E1 favored for that reason. But why is E1 unfeasible? If chloride leaves, what kind of carbocation does it leave behind? For an E1, it leaves a secondary carbon behind, secondary carbocation behind. It's less feasible than the SN2 reaction. And apply the appropriate tiebreaker. I think that's what we're doing here. Tiebreaker. Tiebreaker for SN1E1 reactions. Determine whether heat is added to the reaction. E1 is favored if heat is added. SN1 is favored in the absence of added heat. So let's see. Is it heated? No, it's not heated. Okay, so that's what we're saying here. SN1 is favored because it's not heated. I was looking for another explanation, but that's simpler, actually. If, on the other hand, we have SN2 versus E2 reaction, then what would be the tiebreaker? It depends on whether the attacking species is better as a base than as a nucleophile. So how about this? Well, it doesn't use our example in particular. The attacking species acts as a better base, thus favors E2 over SN2 if it is bulky. Otherwise, both SN2 and E2 remain favored, and you could get a mixture of products. Need a break? Okay. I can wait a few minutes. Let's see. Apply steps 2 through 4 for this same reaction that we've been discussing. I think this is a summary of what we've done so far. Cross out the reactions that can be ruled out. SN1, E1 are eliminated because it's an aprotic solvent. The aprotic solvent would stabilize the leaving group for an SN1, E1 reaction and favor those. Since we have an aprotic solvent, then we eliminate those. SN1, E1 are out. Then we get step 3, the attacking species. A strong nucleophile favors SN2. A weak base favors E1. Well, E1's already been eliminated. So the strong base favors SN2. Step 4 is apply the appropriate tiebreaker. Well, as it turns out, we don't need a tiebreaker. So SN2 is the winner out of this group. Now let's see. Remind myself, what was the tiebreaker? It depends. SN1, E1 reactions. Heat. E1 is favored over SN1, but they weren't even in the ballpark, so we had to throw those out. And then SN2 versus E2. Attacking species acts as a better base and thus favors E2 over SN1 if it's bulky. Otherwise, SN2 and E2 are favored, but SN2 was favored prior to that tie-breaking step because it's such a strong nucleophile. It favors SN2. All right. Now, we're trying to predict the products of a reaction. And this example is SN2 conversion of an alkyl chloride to an alkyl bromide. So an SN2 says that bromide is going to attack the carbon and then the chloride will leave. So the reaction rate here is determined by both the concentration of the attacking species and the substrate, and ideally produce, since it's going to be, it has to be a backside attack, it's going to reverse the stereochemistry. Okay, and that's characteristic of SN2. If it were SN1, then you'd have an intermediate carbocation you could attack from the front or the back. But since this is an SN2 mechanism, you have to attack from the back, and the chlorine leaves. Now the bromine is on the backside, and that switches from an S to an R isomer. I think that was the whole point of that slide. Okay, so in this case, okay, we've got a different substrate. We've got methanol, and that triangle is the chemistry symbol for heat. When you see that triangle all by itself, that means we're adding heat. So, if we have a reasonably strong nucleophile and we have a reasonably strong base, then we have the possibility for all four reactions. And we established that. And we got a good leaving group, bromide. Bromide's a good leaving group. Okay, so we skip over step 1 because we've established that all 4 of them are possible. Then we go to step 2, which is rule out those that are unfeasible. Well, is the SN2 unfeasible? Well, with a tertiary substrate, we've got to get at that carbon, right? That tertiary carbon is going to be sterically hindered. SN2 cannot happen. Right? So we could have an SN1, an E2, or an E1 because we do have beta carbons for the E's, for the eliminations. And with the SN1, the leaving group's going to leave first and produce a carbocation, and then we can attack it. So SN1, E2, and E1 are still feasible. For step 3, we're looking at favored by the attacking species. The methoxide ion is relatively weak nucleophile. It's also a weak base. So that would favor the unimolecular situation, either one, SN1 or E1. The E2 would not be favored because it's not a strong enough base. Okay, so we're stuck with SN1 and E1. So now we need the tiebreaker. How are we going to break the tie between SN1 and E1? Well, notice that we got the heat. We've added heat. which means that the E1 is favored. So this reaction is going to be of predominantly E1. That doesn't mean there won't be others, but the predominant one is E1. And this is what it would look like for an E1 reaction. Once you've established which one is predominant, then you can go to the mechanism and use your curved arrows to describe what's going to happen. Well, in E1, that means the leaving group has to leave first. So what's left behind? We got a tertiary carbocation, which is very stable. And then we've drawn in the hydrogen so that we can show the attack of the base attack. The base attack on that hydrogen then will produce a double bond with the primary, the alpha and the beta carbon, simply by eliminating hydrogen. What's left behind? Well, we've got I'm thinking that cation is not all that stable. So even though we produce that elimination product, it's probably going to decompose anyway. I don't know. We're going to show that. Minor product. Okay. Let's go back. Okay. We said that E1 is the major product, but SN1 can still happen, but it will be a minor product. I think in the previous example, we had roughly 3/4 of it was E1 product and 1/4 was SN1 product. So what would the SN1 product look like? Again, the leaving group would have to leave, and then we would have that very stable carbocation, and it would coordinate, that carbon would coordinate then with the methanol group. Notice that we didn't produce a methoxy group. It's still the methanol group. And that methanol group then would attack from the front or the back. And then we would proton transfer the proton transfer would take place with another methanol group. And that, again, that would stabilize the ether. So you have two possibilities. Two products here are possible: 3-ethylpentene, pent-2-ene, or 3-methoxy 3-ethylpentane as a minor product. And that's primarily due to the fact that we've heated this solution. There we go. Okay, what about this reaction? Another example. Right? Do we have the possibility for step 1 of a good leaving group? Yep, the tosylate ion. Where is it? There it is, OTS. Okay, so we've got a good leaving group. And it's attached to an sp3 hybridized carbon on that cyclohexane. And we also look at the tertiary butoxide ion, which is on the arrow. It's just above the arrow. Sodium is a spectator. So the tertiary butoxide will serve as a good attacking species. So that step 1 says that we're going to have possibilities for all 4. Then we go to step 2. We rule out SN1 and E1 because the solvent is aprotic. So the formation of the leaving group is not stabilized in an aprotic solution. So that eliminates SN1 and E1 for step 2. So we have SN2 versus E2 left over. All right. Let's see. Then we need let's see, do we need a tiebreaker already? Step 3, we identify the tertiary butoxide as a strong nucleophile because it has a negative charge, and a strong base because it's stronger than hydroxyl. Yeah. The attacking species favors both SN2 and E2. So we still are left with the two reactions, and we need a tiebreaker. So what's our tiebreaker here? Well, it can't be heat because we don't have any indication of heat. And in fact, we're dealing with bimoleculars anyway. So we look at steric hindrance. This bulky base will tend to attack the hydrogen and not the carbon. So when it attacks the hydrogen, we favor the elimination reaction. E2 then is the winner. And it's all based upon the fact that our attacking species is sterically hindered. All right. So what we're looking at examples here. Mechanism for an E2 conversion of an alkyl tosylate to an alkene. Okay, so we got a chair conformation there. And the way it's presented, where's the tosylate? Oh, there it is. It's in the front. Okay. Hydrogen's not anti to the leaving group. Okay, we're getting into a discussion here of stereospecificity. Stereospecificity. Specificity. How do you say that? Stereo. Specificity. I was leaving out a syllable. The E2 reaction tends to favor the anti-coplanar conformation of the substrate. So only the production of the double bond, rather than being on the methyl side of the hydrogen, is going to be on the, well, it's the conformation. The hydrogen that leaves is preferred to be anti to the leaving group. That's the preferred conformation. You can get the other, but the dominant outcome is going for the E2 reaction is going to be the carbon-carbon bond is on the, let's see, this would be 1, 2, 3, 4, 1, 2, 3. It'd be 1, 2, 3, between the 3 and 4 carbons. Tosylate is attached to the number 3 carbon. So how about this one? Can we draw the complete mechanism and predict the products for the reaction shown here? In this reaction, R bromomethyl D1 benzene is dissolved in methanol. All right. What does D stand for? Got an idea? It's a hydrogen, but it's deuterium. Yeah. So by replacing a hydrogen with deuterium, now we do have a chiral carbon there because hydrogen and deuterium are different. And this is in methanol. So it's not telling us what reaction it is, right? It's telling us what the stereochemistry is. Is there a suitable leaving group on the sp3 hybridized carbon? Is there a recognizable attacking species? All right. Is there a leaving group? Yeah, bromine's a good leaving group. And how about the attacking species? Methanol. So we expect all four possibilities. Okay. Second, what reactions can we rule out on the basis of the type of substrate? Substrate, solvent, leaving group ability, or the absence of a beta hydrogen. Do we have an absence of a beta hydrogen? Well, yeah, I think so. Well, the problem with that is there may be a beta hydrogen on that phenyl group, but we can't establish another double bond there because that would overburden the carbon. We can't do that. The carbon, we'd have 5 bonds to the carbon, and that won't work. So we can eliminate the elimination reactions, I think. There are no beta hydrogens, however, so we can rule out E2 and E1. Right, we can do that. All right. Then 3, is the attacking species strong or weak nucleophile, or is it strong or weak base? Which reactions do these characteristics of attacking species favor? All right, our attacking species, let's go to the next one. The attacking species is uncharged, so it's not a good nucleophile. It's a weak nucleophile. So that would favor SN1 or SN2. It's weaker than hydroxyl, so it's a weak base and would favor E1 and E2, but E1 and E2 have already been eliminated. So since we've ruled those out, then SN1 tends to win. SN1 reaction tends to win. Right? It's not a strong nucleophile, so SN1 is favored over SN2. That means that we're going to form a carbocation. And then the methanol attacks with its lone pairs on the oxygen and forms a, so where's the bromine? Oh, the bromine leaving. SN1. The bromine already left, form the carbocation. We attack it, form the coordination with the methanol. And then another methanol comes along and removes a hydrogen. Proton transfer. Okay. And since it's an SN1, we get a mixture of R's and S's. Regioselectivity in the elimination reactions, alkene stability, and Zaitsev rule. All right, I think I'll leave that up there for now. So we have 2-iodohexane with a methanol as the solvent and a methoxy ion as the nucleophile or the base, whichever the case may be. Oh, we're going to focus on elimination reactions. Okay, so in this elimination reaction, that methoxy group is going to attack a hydrogen. Which one does it prefer? Which hydrogen? The hydrogen's on the number 1 carbon, the hydrogen's on the number 3 carbon. Right? It's not going to, if this is an E, it's not going to attack the hydrogens on the carbon with the leaving group. So it's either going to attack 1 or 3. There are 2 possible alkene products. And this leads to a competition between hex-2-ene or hex-1-ene as products. Now, the outcome, we're told, at 100 degrees Celsius is predominantly hex-2ene. So in that case, it would have attacked the number 3 carbon. And this produces what we call regioselectivity, which is preference for one reaction over another, reaction sites on the molecule. So let's dig into this a little more. We can look at it in terms of energy barriers. Right? There's a steeper, a larger energy barrier for attack on the number 1 carbon, whereas the attack on the number 3 carbon is much smaller. And also as a consequence, we get a more highly substituted alkene product is more stable. So we got two things going for us here. The smaller activation energy for the number 3 carbon attack and the stability, the lower energy of the hex-2ene. All right. So when we're looking at alkene stabilities, we find that the most stable alkene, the most stable double bond, is the most substituted, non-hydrogen substituted. So we're talking about carbons here. So if that double bond is tetrasubstituted, it's the most stable. Tri-substituted. The disubstituted is roughly, depending on where the substitutions occur, right? The more stable is both substitutions are on the same carbon. The trans is more stable than the cis. And then the least stable is the monosubstituted. Okay. Now let's take a look at why the trans is more stable than the cis. Right, that's on the previous. Yeah, trans is more stable than the cis simply due to steric repulsion. Those substitutions, those disubstituted carbons are going to experience more steric hindrance, repulsion from those groups if they're on the same side of the molecule. So the trans is more stable than the cis. Now, my question is, why did it not explain how both substitutions on the same carbon are more stable than the cis or the trans? Why is that? Because they would appear to be sterically hindering one another. I don't have a good explanation for that one. So what is the Zaitsev rule? Simply, the Zaitsev rule says that for elimination reactions, the product that's produced by deprotonating the carbon atom initially attached to the fewest hydrogen atoms. That's more a practical consideration than it is a theoretical justification. Zaitsev's rule was just an observation that this particular researcher noticed that the elimination product is going to be predominantly formed from the deprotonating the carbon that has fewer hydrogens on it. And in our case, that would have been the, well, let's see. In this case, we're using heat, right? So that does favor eliminations. And the hydrogen is going to be eliminated from the number. There's one produced by deprotonating of carbon atom initially to the fewest hydrogen atoms. Okay, number 2 carbon in this case is going to be the one that is deprotonated. but the double bond could go either way. It could go either in our picture to the left or to the right. But the major elimination product is the one produced by deprotonating the carbon atoms initially attached to the fewest hydrogen atoms. Oh, okay. I'm looking at this wrong. The leaving group is hydroxyl. Well, actually, it's water, right? After we protonate the hydroxyl, then we get water as a leaving group. But in order to do that, we need an acidic environment, and we produce we attack the number 3 carbon, the hydrogens on the number 3 carbon, because it's the least substituted with hydrogens. The number 1 has 3 hydrogens. The number 3 carbon only has 2 hydrogens. And the outcome then gives us a more stable alkene. That's the end story for the whole reaction. The more stable alkene determines which attack is favored. All right. And just as there are exceptions to every rule, here's exceptions to the Zaitsev rule. The anti-Zaitsev regiochemistry occurs with a strong, bulky base. So if we choose tertiary butoxide as our base for the E2 reaction, instead of the phosphoric acid, then what happens is those methyl groups on that tertiary carbon get in the way. And it's difficult to get at that, in this case, that number 3 carbon's hydrogens. So it goes to the more open carbon on the end. And that will give you a higher concentration, higher yield of the hex-1-ene in this case, right? So it's all based on steric hindrance. The anti-Zaitsev regiochemistry occurs with definitely a strong base, but it has to be a bulky strong base. And that way you can choose the outcome. Oh, okay. I think we're going to get an explanation now for why, I hope, for why if you have methyl groups on the substituted carbons, both sides of that double bond, why it's more stable than either the cis or the trans. So if we look at this ethene, for instance, we see that the molecular orbital is effectively isolated. And the empty molecular orbital interacts with filled orbitals from the attacking species. Well, actually, this species has already been, we're establishing ethene versus propene. Okay, so ethene is less stable, whereas propene is more stable. Right? And the explanation is something called hyperconjugation. All right, we get a better explanation here? No, we don't. All right. I don't have the, what I need is the instructor's notes that go with this slide. 9/11. Let me see if I can get those. 9/11. Okay, we've already covered this. The stability of an alkene generally increases with each additional alkyl group bonded to the alkene carbon. That is, the degree of substitution increases stability. Okay. So we know that already. Hyperconjugation comes about when filled sigma bonding molecular orbitals mix with an adjacent orbital that is not completely filled. In the case of alkenes, the unfilled orbital is the pi star antibonding molecular orbital of the carbon-carbon double bond, and the filled sigma bonding molecular orbital provided by the attached alkyl groups. That's called hyperconjugation. Um, hmm. Okay, we're looking at orbital mixing. Without any attached alkyl groups, the pi star antibonding molecular orbital does not participate in any orbital mixing. Okay, so stabilization takes place when you can get some of this orbital mixing, what they're calling hyperconjugation. And the more substituted the carbons, the more of this mixing you can get, which lowers the energy overall. Right. All right. But that doesn't explain why the same carbon having two, well, maybe it does. Let me go back here. If you had another carbon, another substitution on that same carbon, you would not only get mixing with the molecular orbitals on one carbon, but you mix it with three carbons. So that apparently stabilizes it even further. That's the only thing that makes sense to me. All right. Intermolecular reactions versus intramolecular cyclizations. All right. Now we're getting into another, a different ballpark where you can take, we've studied up to this point, we've just studied intermolecular reactions between separate molecules. But you can also get reactions between two separate functional groups on the same molecule. And one of the potential products of that is to take a straight chain and make a cycle out of it. That's an intramolecular reaction. So here we have an example of an intramolecular reaction. Let's see, this is 1, 2, 3, 4, 5. That's pentane. And let's see. Which is higher priority. It would be the alcohol. So it'd be 5-chloro pentane, pentanol, 5-chloro pentane 1-ol. And then we deprotonate it. And that gives us the, so what we have to do is find a way to deprotonate that molecule so it makes a carbon, an oxyanion on one end that can, if we had our models out and we made that, you would see that all you had to do was twist those sigma bonds around and you'd eventually get that oxygen close enough to the number 5 carbon to where you can form a bond between the oxygen and the carbon. And that gives you tetrahydrofuran. That's an intramolecular reaction. And if there's competition here between the straight chain reaction, say between two separate molecules, say we have these molecules in solution, there's the potential for either the molecule to react with itself or to react with another molecule. And if that's the case, the cyclization tends to win. If the cycle is either 5-membered ring or 6-membered ring. 6-membered rings are very stable. And we explain that by entropy. So if you have a loss of molecular freedom, now we're not talking about numbers of products. We're talking about microstates. We're having to get into the true meaning of entropy. So the number of microstates decreases with, let's see, a decrease in entropy would be evident for the tetrahydrofuran versus which is unfavorable. Okay, so that's an opposing factor, right? We're decreasing entropy by forming that ring. So that still doesn't explain why it's favorable. Formation of the ring is favorable. The intramolecular is favored over the intermolecular. Entropy would decrease for the ring structure. But we've decreased the strain. Okay, maybe that's the deal. We've decreased the strain, and there's a possibility that once we form that ether in the intermolecular reaction, then we're also free for that oxyanion on the end to attack a carbon next to the chlorine and form that huge ring, and that would be unfavorable because that would put an enormous amount of strain. I don't know. I can't explain it. It's an incomplete explanation. How about that? All right, this is a case where we're just going to have to memorize. For 5- and 6-membered rings, the intramolecular reaction produces the 5- or 6-membered ring is more favorable than the intermolecular reaction that could possibly occur. Sometimes we have to do that until I can figure out an explanation. I prefer an explanation. Nucleophilic substitution reactions in monosaccharides, the formation of and hydrolysis of glycosides. Okay, I'm not going to spend a lot of time on these because if you're going to go into biochemistry, then you're going to get a snootful of this stuff. This is the type of reaction that occurs in the formation of polysaccharides and tannins. Like the same stuff they use to tan leather, like tannic acids. And if you've ever been to, I don't know, have you ever been to Georgia to Okefenokee Swamp? Yeah. The water is almost black. You can't see through it because there's so many tannins in the water. Okay, what's the formation here? Well, this this acetal functional group forms complex carbohydrates. The acetal has a okay, how do I explain this? Break the word down. Al refers to oxygens, and acid refers to 2 carbons involved. So this carbon has an oxygen on both sides of it, one bonding to the other cycle and one bonding to its own cycle. Some of these acetals can be opened up. And for, say, glucose, that's true. That bond can be opened up, and glucose can appear as both a straight chain and a six-membered ring. Okay, so there's glucose, and there's the open ring structure on the left, and then it forms an intramolecular bond to the number, let's see, I think it's to the, I thought there was a 1, 2, 3, 4, 5. I think we're missing 1, 2, 3, 4, 5. Oh, there it is. I see it. Okay, so the number one carbon is the one with the carbonyl group, and then we number down from there. So 1, 2, 3, 4, 5. So it's between the oxygen bonding with the number 5 carbon, and that leaves the this methoxyl out there by itself, and we see it in the back. Okay. This D-glucose is a possibility. You can also form an alpha D-glucose, but we're focusing on the beta D-glucose. And the beta, I think the idea there is that the hydroxyl on that number 1 carbon is equatorial. And the for the alpha D-glucose, the hydroxyl is axial. Okay, so we can take that one and react it with methanol in hydrochloric acid, and we can form an acetal there. We can put that methoxy group either in the alpha position, which would be axial, or we can put it equatorial, and that would be the beta. So that's known as a glycoside. We formed a bond, an acetal bond at that number 1 carbon. And they typically are diastereomers. And they're always diastereomers. Let's put it that way. I'm not going to get into this too much. Glycoside formation. I think that's a little beyond where we want to be. Yeah. Just described, there are different glycosides in nature. Cellulose forms the beta bond, the beta glycosidic linkage, right? And amylose and amylopectin form the alpha glycosidic linkage. The alpha linkage is, we can attack and digest it with the enzymes in our body. Right? That's why starch is readily available to our system. But it's not readily available. The beta bond is the problem for any organism that wants to digest cellulose. We can't. That's what we call fiber. So termites and other insects have a symbiotic relationship with microorganisms in their gut that produce the enzyme that can break that cellulose apart. So that's why termites eat your house for food. They're not as much a problem up here as they were in the South. They're really active down there. And not only them, roaches too. Yeah. The big guys. Mm-hmm. I took a job with a friend. We were going to cut down this big oak tree. This is in Baton Rouge. It couldn't reach around it, but it was obviously dying. So the homeowner wanted it taken out so they wouldn't fall in their neighbor's house. And when we cut that thing down, it was hollowed out inside, and millions of wood roaches came running out. Okay, so we can acid catalyze the hydrolysis of glycosides. Hydrochloric acid does a really good job and makes a mixture of alpha and beta glucose. And that's as far as she goes.